Hello. All right. Okay, let me see if I started the stream correctly. So I have my study guide, the data booklet. Let me see my audio levels. Does my okay that works. Um, and the Google. Okay. So let me see. I'll start the stream when I get confirmation that I did this correctly. Huh. You here? Okay. Is there anybody watching? I don't know. Huh. Two watching now. Yes, thank you, York. Hey, shout out to my biggest fan. Savi. Hi, thank you. Okay, so alright. So okay guys, today I will be reviewing chemistry starting from structure one. Two watching now. Yes, thank you, York. Hey, shout out to you look really good. Thanks, Savi. Yeah, but so today I'm going to be using this Oxford study guide, and I think it's like really helpful. It's like basically the textbook, but it's like just better. And I'm too like lazy to do any of my own resources, but yeah. And if you guys have like any questions or anything you want me to like cover first, just tell me in the chat. I'll try to keep an eye on it, or like any questions you want me to cover, or else I'll just be going through this slowly, and you can like put it on standby and think like, oh, did I listen to this like content before or anything? Yeah. But yeah, I'll start by talking about the separations of mixture. So that's all the way back to structure one. I think I put a list of other things in the description of other videos on IB chemistry because this exam will go through everything before, but I guess that's all right. Okay, so first of all, separation of mixtures. So I think this is more of like a 1B thing, but there's a few ones you need to remember. So and you gotta know evaporation and distillation and separatory funnels and using like melting point. So you gotta know like the how you're separating these mixtures and like what property are you using to separate this. For example, if you have a filter, you're using the size. If you're using like crystallization, you're using like its temperature curve, the heat thing, right? And the thing here, and I actually like I predict this might be the 1B because there's only so many 1Bs that she has like talked about, and chromatography is one of them. So is there actually anybody watching? One. Oh, well, my stream isn't. Would you provide the link to the textbook to everybody? Yeah, of course. Um, oh, you got downloaded. It's on Google Classroom though. It's Miss Kilson did give it to us. So I'll go to my Google tab. No. Oops. Nope. My Google tab. Google tab. All right, that's right. Go to my Google tab, and so it's I think it's here, digital textbook, and you want to click this Oxford course companion chemistry, and you need to open it in a new tab, so you can download it. Download it, and if you download it, you'll get the thing here. So I'll put the Google Drive. Let me see. Who is this shared to? What? I don't know how I can share this, but it's on Google Classroom, you guys. Can we go over potential paper 1B topics? You don't want to get a 3 again? Me neither. I got a 3. That was horrible. Yeah. So, paper 1B. I think it's also on Classroom. So, yeah, if you want to, I can go through that first. So let me try to remember where she gave it. Here. I also need to download it. Damn it. All these download. Oh no, I don't need to. Okay, so today at the parent teacher conference, Daniel asked her about a lot of things, but so I'll go over every single one of the topics. So first of all, like the solution preparation, and over here I think I'll switch to my iPad. Here, does that work? Yeah, it does. All right, let me switch to a new tab. So the first thing you want to be careful in a paper 1B. So let me just label it so the people that just joined the stream will know. Paper 1B preparation. You know. Okay, so I think it's either gonna be like separation of mixtures again, or it's gonna be like the chromatography. And the reason I think of this, but chromatography is also kind of like separation of mixtures, if you know what I'm talking about. So separation of mixtures and chromatography. I think my chat isn't updating correctly. Do I need to go back to check? I don't care enough at this point. But yeah. So if we move back to this tab, actually I think this document does a really good job of like telling you like what you need to do, and these are like the common mistakes that we make. So I think it's less of like um about what you might not write enough. Um, it's more of like what you might accidentally like write that's wrong. So for example, I don't know, man. 1B is just really harsh and Miss Coulson is just like ruthless. So over here, like you need to have like specific improvement. I don't think we'll go into so deep as that, but okay. So this is titration and gas collection. We did this one, yeah. Why is there only? Oh, I didn't change this to public. Oh no. Did it work? Oh no, that's right. Oh, that's really stupid of me. Okay, so this should be a public stream now. Do you guys mind if I just go in? Whoops. And like check if this is actually public. I am live and really stupid of me. There's even less people watching. Oh, that's worse. Yeah, but I guess I'll just keep talking until somebody stops me. This one. Okay, so about gas collection method, I think this one's like one of the easier ones. So you just need to remember the PV equals nRT, and we covered that in structure 1. So the correct procedure for the syringe one is that when you move a plunger freely in a barrel, why am I reading this? Basically, just like say like the volume that you read is for any gas, because you're displacing the water, right? But you have to be careful with those like gases that can actually mix with water, because you cannot use this. But this is like, just think of it as like the gases that cannot mix with water, and then you're displacing water to find out how much volume of gas that you're actually displacing. Okay. Anyways, um I'm not really sure how I should go about this. Do I keep talking about like paper 1 stuff, or do I talk about the content? Because I don't know about 1B. I don't think you can really prepare for it because there's only so many ones, and you just gotta like kind of understand all of them. Anyways, I don't know if you guys remember about the kinetic molecular theory and a change of state. So um I don't really think this will come up, but it's good to know that, everything is moving, and the temperature is that the energy of the particle is basically the temperature. And the change of state occurs when the energy of the particles is exchanged. So you need to know like, oh, is it melting? Is it freezing? Is it boiling? Is it expanding? Is it sublimation or is it deposition? And this chart right here, I think it will come up because it's not just used about like this kinetic molecular theory, but about other things as well. And that connects to how the distribution of molecular velocities go. So I think I directly. Oh, they also have the multiple choice questions here. Um, should I go through any of them? Um, do you guys remember how they like calculate the R values of the components? It's like you gotta take the length of how much it has run divided by the entire length of the solvent that the solvent has run. So you get that by finding like the cohesiveness of this particular liquid and the things that you are dividing it by. So yeah, the cohesiveness, what I'm talking about, chromatography is like a really interesting unit here. And if we go, what else should I talk about? This is going very poorly. Hi chat. Oh my god. Hi. Oh right. Oh, I don't know why like my stream here isn't like updating properly, but yeah, it's okay. The audio is okay, right? Yeah, but I'm still covering from structure one, so I'll just go in order and there's like you guys have something particular that you want me to talk about. So I think it's a good time to review PV equals nRT. I don't like how thick this is. PV equals nRT. So I also have a textbook right here, but I think I'll just talk about it. So when you see PV equals nRT, like just think of it like PV over T. This is going to be a constant for most situations. When like the only thing that is changing is the molec uh this is all going to turn into a constant, right? Given that the mol the moles and well the definition of the R is already a constant. So what you're thinking of is when you increase the volume, what effect will it have on the pressure or the temperature? And because it's like being a divider, you could even just keep moving around PV equals T, right? Because the N and R are basically constants in most situations, unless you're like adding things, but that's not gonna come out. So when you see like, oh, for example, like when the pressure goes up by 2, but the temperature stays the same, what will happen? You need V2 because P and V, the temperature will stay the same, so V would equal 1/2, right? So these are the type of question that comes up, and you can either be changing the volume of it, the pressure, or the temperature of it. If you're changing temperature, I'm pretty sure it's called Charles's law, but yeah, that's the ideal gas equation and the stuff that it entails. Lagging so bad, man. Hope okay. No, I'm getting XP. Savi, I can't read this chat in time. Charles, do you have any equations on balancing equations faster to gain time? Oh, where's the. I can't read this in time. Or there are people on the top with crowns. Wow, open it. I'm leaving it. Sorry, I'm trying to read the chat. What? How? Okay. Oh, I think I need to be on this tab for the chat to work for me. Yeah. Oh, okay, to answer York's question, yeah. Okay, I don't like how I need to be on that window for the chat to work. But okay, for example, we're balancing equations, right? So I know Miss Kilson tells you to like line up like, okay, this is for how many carbons, this is for how many hydrogens, and then you need to like keep comparing them. And like that's kind of like, well, for me anyways, I don't think it's the best method. So I'll go to Google Classroom and we'll pull out the balancing equations together. Let me go to Google. Google window. Yep, that worked. Google window. And what is that? Gas law math? Is it? No. What's balancing equations? This one. This one. But this one's pretty easy though. What did I do here? Oh, okay. That's, for example, AL plus CuO. Let me write it first. AL plus CuO will become Al2O3 plus Cu. Okay, to answer York's, let me go to the iPad. All right, so we have this equation, right? And they're gonna give us all the elements that we need to know. Can't stand stickers. Can you do more dimensional analysis, Charles? Dimensional analysis. Yeah, sure. Okay, but anyways, let me just finish like balancing this one equation before I move on. So, for example, here I would see like one element that only appears on one time. So I would set like how many x here into like x of AL, right? But over here you need there's AL2. I wrote that wrong. AL2. But so over here you're you're gonna have to have, let me get a different color. You're gonna have half of X, right? Because you have two aluminums per molecule, so half of all the aluminums times two is like all the one times X. And when you see X over two, but there's three oxygen for every X over two of molecule, right? I mean, I use variables here, and I think for the start it might be like a little not as intuitive, but I think it actually helps out in the long run. But over here you will see like there's one oxygen per CuO, right? 1O. But you have 3x over 2 oxygens here. And if you have 3x over 2 oxygens here, you would need 3x, because there's one copper on both sides, you'll need 3x over 2 coppers on both sides. But when you're balancing equation, you always trying to find like the you cannot have any fractions, right? So you look at like what is the largest degree of fraction. So in this case it's 2. So you multiply everything by 2. Like if x is equal to 2, then everything can be a whole number, right? 2 and 2. So the answer here, if you set x to 2, the answer will be 2 aluminum plus 3 CuO copper oxide plus aluminum oxide. So 2 over 2 is going to be 1, and you don't need to write that. And 3x over 2, when x is 2, is still 3. So yeah, that's how I do balancing equations, but faster. And